Welcome to lesson 4.3, where we are going to talk about the first half of graphing rational functions. Now, graphing rational functions has 7 steps. Today, in this lesson, or the next few videos, we're going to talk about the first 5 steps to doing these graphing of rational functions. In the next section, 4.3b, we'll discuss the last 2 steps. So, first step, anytime I'm graphing a rational function, is always to simplify if I can. That is always the first step. Simplify if you can. So I'm going to look at my equation here and try to simplify it. That means factoring and GCF, and if there's no glue terms, factor tree. This one does have a glue term, so I'm talking about GCF and factoring. If I look at the numerator, there's no GCF in that, and I can't factor it because it's not squared, so I don't have to do anything for the numerator. But for the denominator, I could factor that. So I'm going to factor this. So I need 2 numbers that multiply to -6, add to -1. So I think that's going to be -3 and +2. And now I've simplified it as much as I can. Check. Step 2, find the x-intercepts. I'll find the x-intercepts by setting the numerator equal to 0. That's how we find our x-intercepts. So I'm going to take my numerator, set it equal to 0, and solve it. So I get x equals 1. And we will always write our x-intercepts as a coordinate point of number, comma, 0. So I'm going to take this x-intercept of 1 and write it as a coordinate point. Check. Step 3, y-intercepts. To find the y-intercepts, you set x equal to 0. So I'm going to look at my equation, and anytime I have an x, I'm going to substitute it for 0. So I have a 0 minus 1, and then I have my parentheses. Looks like I have a 0 minus 3 and a 0 plus 2. If I simplify this, 0 minus 1 is a -1. 0 minus 3 is a -3. And 0 plus 2 is a +2. I'm going to multiply those together because of the parentheses. Parentheses means multiply. So I'm going to get -1 over -3 times 2, which is a -6. And then I have 2 negatives, which will make a positive. And I always write my y-intercepts as 0, comma, a number. So this one's going to be 0, comma, 1/6. Now, before I move on, as we do each of these, we should also be graphing them. So I'm going to take these 2 coordinate points. I have 1, 0. I'm going to graph that point there. And 0, 1/6, graph that point there. Check. Step 4 is your vertical asymptotes. I'm going to shorten that. To find a vertical asymptote, you set the denominator equal to 0. So now I'm going to look at my equation and take the denominator. In this case, I have 2. So I'm going to set them both equal to 0. For both x-intercepts and vertical asymptotes, if you have more than 1, you just set them all equal to 0. And there's my vertical asymptotes. Vertical asymptotes are always written as x equals a number. So I can just leave them like that. And they're graphed using a dashed line. So I'm going to go to +3 and do a dashed line through +3. That's one reason it's called a vertical asymptote. because it's a vertical line. Okay, so far so good. Step 5, the last step that we're doing in this lesson. Step 5 is our end behavior. This is probably going to be the weirdest one. Now, if you remember, end behavior was something we did last chapter. And it was the chapter where we had like the smiley face, and then we'd say the end behaviors are both going to infinity. So then when I went to graph it, I would circle the top 2 corners, and then I do my crossing and bouncing thing and have my end behavior. And how we talked about your end arrows should always point towards your end behavior. Similar thing here. This end behavior is going to tell us what the end arrows do. But a big difference from last chapter is this time, instead of going up or down, our end behavior arrows are going to go to the side, which is a little different than what we've been doing. So when I talk about end behavior, there's a specific thing we need to do. First off, there are 2 types of end behavior that we're going to be doing in this class. To find which of the types this problem is, you look at the degree of the numerator and the degree of the denominator. So just a reminder, degree is the biggest exponent. So if I look at this numerator, the biggest exponent in that numerator is a 1. If I look at the denominator, this one's written differently. And we talked about last chapter, anytime it's written with parentheses, instead of just written out like this, if you have those parentheses, you need to take your exponents and add them. That's how you come up with the degree if it's written with parentheses. If there's no parentheses, you just look at whatever the biggest one is. If there are parentheses, you've got to add them all together. So I've got 1 plus 1, so that degree is 2. So here's my first end behavior rule. If the degree on bottom is bigger or greater than the degree on top. This is my end behavior rule number 1. If the degree on bottom is bigger than the degree on top. If that's true, then your answer, or I should say end behavior, is always 0. Period. If the degree on bottom is bigger than the degree on top, it's always 0. Now, I always write my end behavior as y equals a number. And if you remember, last chapter we used like limit as x goes to infinity and limit as x goes to negative infinity. That was last chapter. This chapter we always write our end behavior as y equals a number. And since my degree on bottom is bigger than my degree on top, my end behavior is going to be y equals 0. And the way I graph that is I take my circles like I did with polynomials, but instead of in corners, my circles are going to go off to the side at 0, or the axis. So if you ended up getting like y equals 2, a number, which is like something we'll do in the next problem in the next video, you would go up to 2 and put both circles at 2 on the side. So that is all 5 steps for our first rational function. I usually call these steps the bones or the skeleton of the graph because they kind of give you a structure for the graph, and then in steps 6 and 7 you actually fill in the graph, you graph it. So in the next video we'll do a couple more examples of finding all these different pieces.